Okay, vectors. We are now going to begin talking about objects moving in 2 dimensions simultaneously. So in the previous chapter, we were talking about one-dimensional motion. So our objects were either moving in the vertical direction or they were moving in the horizontal direction. Now our object is going to be moving along both axes at the same time. So 2-dimensional motion. Okay, let's make sure that everybody is clear on the vocabulary word scalar. This is a quantity that can be measured completely by simply expressing a magnitude and then providing the appropriate units. Make sure that you understand that all measured values in this class are going to have units to go with that measurement. So when we say that a variable is a scalar variable, we're saying that it is simply expressed with a magnitude, just a number. So it will not include direction. We will not have positives and negatives. So in this class, we've already talked about time, distance, speed. Those values are always going to be expressed as positive because the direction is not indicated with a positive or negative. Things like volume and the number of pages in a textbook, those would all be considered scalar quantities. Vectors, on the other hand, are going to be values that have a magnitude and also include a direction. So when we're speaking numerically, now our values are going to be either positive or negative in order to represent the direction. We're also going to be able to illustrate these with arrows, where obviously the pointy end of the arrow gives us the direction. And the length of that arrow is going to be used to represent the magnitude or the value of our variable. The resultant is a new vocabulary word that we have not discussed yet, and this is basically your outcome. Obviously, your result, the overall effect of combining multiple vectors. When we talk about combining vectors, we're talking about graphically representing them. So we have illustrations here where we are showing how to properly connect our vectors using what's called the tip to tail rule. I actually prefer to call it the nose to tail rule because I think of the arrow as being the pointy nose in the front of somebody's face, and the nose always points in the direction that they are facing, right? The direction they're moving. So nose to tail or tip to tail, whatever you want to call it. If the vectors are moving along the same axis, in other words, if they're both vertical vectors or they're both horizontal vectors, you're simply going to add them together. So visually, graphically, we would take our vectors and we would connect them so that the nose or the tip of the first vector is where we begin drawing the tail of the second vector. So here you see some vectors that have already been combined. So in this first example, if I have this as my first vector, I am going to say the tip of this vector is where my second vector must be attached. And so indeed, that is what I did in the illustration over here. Now, as far as my resultant goes, the outcome, the overall effect of me doing that, we're basically going to say that numerically, we are adding our vectors or our values so that we get a bigger number if they're both moving in the same direction. We would be subtracting our vectors, or we would be combining positives and negatives if they were in opposite directions so that we get a lesser value. So graphically speaking, we would illustrate that with a resultant vector that shows the overall result of our vector being larger or smaller now because of that combination. And so here you have some examples. We have a representation here of a vector on the left, or a vector set, where they are both moving in the same direction. And so we can see that they've basically given us a formula where S1 and S2 are my two vectors originally. They're asking us to add these two vectors together. On the right-hand side, notice that they're still asking us to add them for our formula. But now you need to remember that negative vectors or vectors that are to the left or down are going to be expressed as negative numbers. So although the formula that they provided still says for us to add these vectors together, you can see here this is going to be some negative value for my second vector. So some people say plus a negative, other people like to say minus the second vector. It's whatever you are most comfortable with. I'm just going to say be very careful that you are accurately representing how those values should be combined, okay? All right, here we are talking about graphically representing vector addition where the vectors are not parallel. In other words, they are not along the same axis. So if we look at this illustration to the right, you can see that we have two vectors, S1 and S2, and so they have combined them for us so that they are connected nose to tail. But I want to point out to you that our resultant is going to start at the tail of the first vector, and it's going to end at the nose of the second. So my resultant is also a vector so that it has a magnitude, but it also has a direction. It's very important that you understand that your resultant also has a direction. So when you illustrate that for me, you must make that resultant a vector. Do not make it a line segment. And it will also need to appropriately take into consideration the directions of the components so that we can get that correct overall value. Because they are not along the same axis or parallel, we are going to need to do some trig here in order to calculate that overall resultant value, or maybe take a resultant and break it up into its components. So here we have a couple of right triangles. The acronyms SOHCAHTOA are there to help you remember what the formula says about how to calculate those missing pieces. So sine opposite hypotenuse is what the acronym SO stands for. And so the equation here says that we would take the sine of our known angle, and we're going to set that equal to the opposite side divided by the hypotenuse. So that's where the SO acronym comes from. Sine theta is equal to opposite over hypotenuse. And you can see that we work our way through the different acronyms in order to determine what those other formulas should be. Now let's make sure that you understand how to determine what is the opposite side or what is the adjacent side and what angle are we referring to. So on our right triangle, obviously we have to have one corner that is our right or 90-degree angle, and that's marked here in green. We need to have an additional angle that becomes our point of reference. So in this particular diagram, I have my known angle, or my angle that gives us our point of reference, is located in the bottom left-hand corner, and that's highlighted here in yellow. So whenever we are trying to determine what value should be input as the opposite piece of my formula or the adjacent piece of my formula, it's going to be based off of what corner my known angle is located. So if this is my known angle, in this case side A would be located opposite from that known angle. If this is my known angle, then side B would be located adjacent, meaning it is part of, it shares that side that makes that right, that makes that angle, sorry. My hypotenuse is always going to be located opposite from my right triangle. That will never change. You can see I have a second triangle here. Just to reiterate that we have to assign our opposites and adjacents according to my known angle. So in this case, here is my opposite side. And then here is my adjacent side because it is adjacent to that known angle. So make sure you understand how to identify opposites and adjacents. Once again, hypotenuse is always the long side and it's opposite or across from that right angle. If we're trying to do math work and we have two of the sides that are known, then we would simply use Pythagorean theorem in order to calculate the missing or unknown side. All right, so here I have an example problem that I've already worked, but I'm going to erase this and go through it with you so that you can understand where all of those values came from. So this word problem says that we have a triathlete and they are going to travel south for 483 meters and then they're going to swim horizontally for 225 meters. What is the magnitude of the triathlete's resultant displacement? So initially my triathlete is going south for 483 meters. Then it doesn't tell us which direction horizontally. I'm going to just choose a direction for 225 meters. Now I want to pause right here and I want to point out that my horizontal vector is intentionally drawn shorter than my vertical vector. If that's not clear, if they look like they're close to the same size, but they should be different lengths, then you need to please fix your illustration or fix your diagram. So to make it clearer, I'm going to draw this so that's a little bit shorter. Now, how do I know how short it should be or how long it should be? If I'm working on graph paper, then I'm going to use the grids in order to help me determine what those lengths should be. If I'm doing something like this example where it's just on plain paper, I need to basically do my best to draw them to scale. So 483, 225, it's about half the length for the second vector than the first because it's about half the magnitude. So if you are not illustrating your vectors proportionally, then it can and most likely will cause some problems for you in understanding or interpreting what that resultant should look like. And it will also affect how you pull your values and input them into your math work. So make sure that you are illustrating these properly. My resultant then is going to be the overall outcome after I've combined these, and so here is my resultant piece. Now, if I'm trying to calculate this, I'm obviously going to be using Pythagorean theorem because I have two sides and I am just missing the third side. So I'm going to say a squared plus b squared equals c squared. That is my Pythagorean theorem. My A side would be my 225, my B side would be 483, and then my C side is always my hypotenuse. Now, when we go to solve for this, we're going to plug in 225 squared plus 483 squared, and that is equal to c squared. Now, I expect you guys to understand that I'm going to have to square root my c squared in order to get that to equal just plain old c. And that means that I'm going to need to do the same thing to the other side. I would like for you to begin practicing going ahead and setting up your math problems like this so that you can now take your calculator. It is one entry, square root, open parentheses, 225, hit your x squared button please, plus 483, x squared button, close your parentheses. It's one entry. You get one answer. It's so much faster this way, and you are less likely to make mistakes because you are retyping, rewriting, or copying numbers over and over again. So here's what I get in my calculator. Now this answer needs to be rounded for sig figs. So I'm going to get 533. My units for my final answer here are going to be expressed in meters because the values that I was given for my triangle, the values that I input into my calculations were meters. Your triangle is basically one variable at a time. Okay, so if my sides are displacements, my resultant is displacement. If my resultant or my hypotenuse is velocity, then the components or the x and y axes are going to be also in meters per second for that velocity. Okay, now I want to take a moment and I want to rewrite this so that you guys can see how Pythagorean theorem would translate more appropriately for the vocabulary that we're going to be using. So if we're looking at our triangle and we are using the vocabulary that is appropriate for this topic that we're currently in. Our hypotenuse would be our resultant, right? So the resultant value was 533 meters. Now, if we are solving a problem, we'll probably ask for the displacement. So you may say x equals, but what we have solved for is the resultant side, right? So that would go here. My A side and my B side in math class, don't think they really give you set rules on how to label which is which. Because we are going to be speaking in terms of vertical and horizontal, I like to be very consistent as often as possible. It leads to less confusion, both for me and for my students. So I typically say that the A side is my horizontal side. So that would be this x-axis. My B side then would be my vertical side, and so that would be the y-axis. And so if I were to rewrite my Pythagorean theorem so that it matches our two-dimensional motion, then it would look something like this, okay? All right, now I do want to go ahead and do a bonus problem with you. If you would take a look at your practice work for the first assignment, it's titled Finding Resultant Vectors. And question number 1, I'm going to go ahead and work through that problem with you right now. All right. So question 1, I'm going to take a second and find some empty space here. Question 1 says that we have an ostrich that is running east, and it is traveling for 7.95 seconds. All right, now it says that it's going to then run 161 meters south. The resultant displacement is provided for us in this problem, and they tell us that the resultant is 226 meters. Okay, so I know my resultant value. All right, calculate the magnitude of the ostrich's eastward component and its running speed. So the first thing I'm going to do is I'm going to calculate this component. That's what it asked me for, the magnitude of the eastward component. So x is the horizontal direction. I am also, as it turns out, looking for x as in my displacement. How did I know that finding this side is going to give me my displacement? Because the other two sides of the right triangle were displacement. Okay, so the first thing I'm going to do is recognize that I have two sides of a right triangle. So Pythagorean theorem, it's going to be my hypotenuse squared plus the horizontal component squared plus the vertical component squared. Okay, so in order to solve for the x-axis, I need to do some algebra. So once again, I would like for you to begin practicing rewriting your formulas before you plug your numbers in. And then we know we're going to have to square root here. So let's square root there. So this is how I'm going to set up my problem. My displacement in the x direction will be the square root of 226 squared minus 161 squared. I'm going to put that all in my calculator, one entry. Real quick and easy, no rewriting anything. And that gives me 158.603, and then there's more digits in my calculator. This final answer will be rounded to 159 meters for sig figs and with the appropriate unit. Now the second part of this question asked me to calculate the running speed. So let's go back to the original problem. These values given on my triangle are displacements, but this time up here was given to me as well. So my time is 7.95 seconds. So if you recall, we said that the velocity is displacement over time. So I'm going to say that the velocity, or the speed in this case that they are asking me for, is going to be my displacement. So notice that I am using the unrounded value. Please ask your calculator to use the previously calculated answer with all of the decimals. So your calculator should have an answer button. I would like for you to utilize that answer button. I do not want you retyping, and I do not want you using the rounded answer of 159. We need to use the 158.60 blah 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 blah. We want all those numbers, okay? Divided by the time that they gave us is 7.95 seconds. We put this in our calculator and we get 19.9500, and once again there's more digits. When we round this for sig figs, this is going to round to 20.0. I've calculated my velocity. This was meters and that was seconds, so meters per second. So the velocity in the horizontal direction, which in this case was to the east, is a value of 20.0 meters per second.